So this video looks at operating systems. This is 5.1 in the CIE A-level specification. It forms one of a series of videos for the whole AS and A2 course. So please check out the other videos if you're doing this course. So why do computers need an operating system, and what is an operating system? Well, let's start with computers. Computers are very complex hardware now. We have flexible general purpose computers. Lots of devices might be connected to them, so it's a really complex setup of hardware. So to manage that hardware effectively, we need some software to help, and that's system software. And the system software we use to manage the system is called the operating system, and it allows users and applications to actually make use of the complex piece of hardware. So the operating system is hiding complexity from the user and from applications. If we didn't have an operating system, the user would have to communicate directly with hardware, and every program would need its own code to drive the disk, the screen, the keyboard. So that's a lot of duplication of code. There wouldn't be a file system. You'd have to just have the data as raw on the disks or on the secondary storage. So you'd have to manage accessing it, and you'd have no help. Only one program could really run at a time because there would be conflicts between programs trying to get hardware resources. Things like memory, they'd be conflicting over trying to get the same thing, part of memory, for example, if there was nothing to control it and manage it. So you'd have no access control, no error handling, no user interface. So it would be very difficult to use a machine without an operating system now. So with an operating system, you'll get the user interface. That could be a graphical user interface or command line interface, or sometimes you see menu-driven interfaces as well. It provides a platform on which application software can run, and it manages and shares the hardware resources between programs if you've got multiple programs running at the same time. And it handles all input-output through device drivers. So input-output to peripherals is done through a device driver. A device driver is a piece of software that understands the device and understands the computer that you're running on and translates in between. And it deals with errors and protects data from unauthorized access. A good thing to say in the exam about the OS is it provides an interface between the user applications and the computer hardware. So we can view it like this. We have users that are typing, clicking and tapping the screen, and we have application software like word processors, browsers and games. And they sit on top of the operating system. So the operating system is there in the middle between the users, the applications, and the actual hardware underneath. And to access some of that hardware, like peripherals, we need device drivers because they can all vary. They're very different. Every single peripheral could be different. But for things like CPU and RAM, we don't actually need device drivers because they're standard and the machine itself understands those directly. So operating systems have 5 main tasks that you can list. These are memory management, allocating RAM to processes that are running, keeping the RAM safe and separate between those processes, tracking where things are in RAM. File management, looking after directory structure, naming files, moving, deleting them, and maintaining access rights to files, like defining what the access rights are. And then security management, so the ability to have accounts with passwords and usernames, be able to define separate access rights to be on the type of user, for making sure that security updates are done and potentially encrypting your data. So some operating systems will encrypt data by default. And number 4 there, hardware management. So looking after the actual devices, so using drivers, buffers between devices and the computer, handling interrupts, queues for things like peripherals. It's like a print queue, for example. So managing those things. Number 5 is process management. So a process is task, a program that's running and its associated data. So it has to manage that process, has to schedule them, decide when they're going to run, allow multitasking, allow more than one process to be running, even on a single CPU, and avoiding situation where you get deadlock. Deadlock is where two different processes are trying to get the same resource, but they're both holding on to them. So they're in a stalemate. Neither of them will release them, and the other one needs them, so that neither of them can get anywhere. A way of memorizing those 5 is with MFSHP. My files should have priority. MFSHP, memory, file, security, hardware, and process management. And of course, in addition to that, you've got things like the user interface that the operating system provides. So let's have a look at memory management a bit more. Decide which process is going to get the part of the RAM and protecting that process within its memory area. So it allocates memory to each process when it's loaded, and it reclaims it when the process ends. So that memory is then freed up for another process to use. It keeps a record of which memory locations are in use and which are free. Protects processes from each other. Enables multitasking because it allows several processes to be held in RAM at once, and keeps track of it all so that they don't mess each other up. It may use virtual memory. Virtual memory is a process whereby some pages in RAM are swapped out to disk, to secondary storage, when RAM gets full. That allows more space in RAM to be freed up, and then another process can be swapped in and run for a little while, and then swapped out again, and something else comes back in, and so on. So we keep using secondary storage as a swap out area, and then we can bring things into RAM, give them some time. That way we can keep tasks running. It's like trying to spin plates, trying to keep them all running a little bit, even though you don't have enough RAM to fit them all in at one time. It uses things like paging, where the fixed blocks of memory are allocated to processes, or segmentation, where variable size blocks. And we come on to that more in year 13 for the A2 part. Another management task is file management. So this gives users a logical view of the storage instead of having to look directly at raw disk access, for example. They can it doesn't matter how it's physically stored, they will just have a logical view of data. So it maintains a directory structure and enforces naming rules. It creates files, opens, saves, renames, copies, moves, deletes them. Records where the file is actually physically stored for you, allocates free space and keeps track of it as files grow or are deleted, and then enforces the access rights to make sure that you can read or write, or don't have any access at all, and so on. And it maintains metadata. Obviously, metadata is data about data. So about your data file, you would have some metadata, like the type of file it is, how big it is, who owns it, when it was created, and so on. All the sorts of things you see when you list files in an operating system. Then security. So security is there to protect data from loss or damage, unauthorized access. So various ways of doing this. You can have user accounts, where you have to have a username and a password to get access. You can set access rights, so different people have different levels of access, so it keeps more sensitive data safer because less people can access it. Making sure updates and patches are applied to make sure that vulnerabilities are patched and your system is not at risk from them. It does recovery and backups, so it will have system restore points, so in case you get damage or a problem on the system, you can go back to a recovery point. It will have firewalls, anti-malware software. Firewalls filter traffic, so packets of data coming in and out will be checked and possibly filtered by the firewall. Anti-malware software or antivirus software, this will make sure that your system is not infected, or tries to ensure it isn't. And then finally, encryption. This helps obviously with security, because even if your data is accessed, people can't understand it without the key. Then we have hardware management. So these input and output and peripheral devices, these are all handled through drivers. The buffers are implemented and interrupts are handled with the OS. So a driver is just a piece of software that sits between the system and the peripheral and understands both ends, so acts effectively as a translator, putting messages in the format that the device can understand. Because these devices can all be made by different manufacturers, work in slightly different ways, it's impossible to create a system that would be able to handle all of those with its built-in code. So it needs to be able to have access to device-specific drivers that helps it to communicate with them. And buffers, obviously, because devices may be working at different speeds. The CPU may not be able to, or may be able to output data much faster than the device can handle, so it needs to be placed in a buffer before the device accesses it. And of course interrupts to let it know when devices are ready, and so on. So each peripheral might have its own device driver. It controls the sending receiving data to and from those peripherals, handles the buffers, the interrupts, manages queues like print queues. So for example, at the bottom there we have the application wants to do something. It asks the operating system, that might go to the device driver. The data might go into a buffer and then eventually end up at the peripheral. And the peripheral may raise an interrupt when it's finished, and it'll go all the way back again, back through the buffer, through the device driver, back to the operating system, and back to the application. And then we've got process management. So there may only be one CPU in a system, but many processes that want to run, and the users want to feel like they're all running at the same time, even when they're not. So in order to do this, we need process management. So a process is just a program that's in execution, together with its data and its current state. And a scheduler within the operating system decides which process is going to use the CPU next and how long they get. So in multitasking, processes take rapid turns. So they get a short burst of CPU time before another task, or process rather, is brought in, and then that gets some time. And for the user, when this is running smoothly and quickly, it appears as though those processes are running simultaneously, even though they may not be. They may be just getting slices of a single CPU. So the idea is to allocate CPU time and other resources fairly in an efficient way. It needs to avoid deadlocks where two processes hold the resource that the other one needs. And it keeps a process control block recording the state of each process when it's swapped out. So it remembers what it was before it was swapped out, and then can pick up again and run when it restarts. You may see sometimes process state diagrams drawn for this kind of thing, but again, that's more detail that will come into next year. So the operating system also often comes with utility software, and utility software is software that performs housekeeping tasks. It's part of system software, so an operating system and utility software they're both considered to be system software. But the utility software is there to perform housekeeping tasks. It doesn't really do things that the user wanted to do, like the user wants to create, say, a spreadsheet or create a document. They didn't want to do the things that the utility software does, but it helps keep everything running efficiently and safely. They're often in the background. The user may not even be aware of them, but they're still running to make sure the system works fine. So the first one we've got there is a disk formatter. Then we have virus checker, defragmentation software, disk content analysis and repair, file compression, and backups. Let's have a look at these. So disk formatter, analysis and repair is to prepare a disk for use, we need to format it first. And then to work out what's gone wrong with it, we might need to analyze it and then try and repair it. So the disk formatter organizes the disk into a structure that the OS can use. So it creates tracks, sectors, and a file system. You may be familiar with some of those file systems. You've seen them before on your device. When it maybe asks you how you want to format a disk, you can tell it which format you want to do. It will create the directory table so files can be stored and then found again, and erases any existing data, so it must be used with care. I mean, effectively, it doesn't actually really go through and erase everything, but it gets rid of all the directories and everything, so you can't actually find any data that you had there before. So effectively, you can't use it. Disk contents analysis, that will look at the storage and see how the space is being used. Might look at the type of files, the folders, the size. Can identify very large files or duplicate files and maybe suggest removing them to free up space. And then disk repair, that can scan for corrupted or unreadable sectors and lost file fragments, and then report that and then try to do something about it, fix it. It can mark bad sectors so they're not used again and recovers the data if possible. So defragmentation software is software used with hard disk drives because over time, when files are deleted and new ones are created, we end up with files that are separate. They're like disjointed and split up over across the disk. Because this is a physical storage medium with a read-write head that has to find the parts of the file when it's reading or writing to them, then that means that the read-write head is going to be hunting around for lots of different parts of the disk to get the file it needs. So defragmentation moves the fragments of files so that they're all together again, and that means that it can free up some space into big blocks that can then be used to write files. So it makes an existing file store in one place, so that's reading it is going to be more efficient. Once you've found the start of the file, you can read through the file without having to skip around the disk. But also when you want to write a file, you can find a big enough gap to write it into, and then again you can just write it all in one go. So this results in faster file access and faster loading of programs. So after a while, defragmentation of a hard disk drive may improve the performance of your system. Obviously this is not used on solid state drives. Partly there's no moving head to hunt around for different parts of the data, and if you were to try and rearrange files, then the extra writes would shorten the drive's life. Then we've got a virus checker, or sometimes called antivirus software. This is for detecting viruses and quarantining them, or potentially removing them. So you can use scan. A scan will check files, memory, and incoming data against a database of known virus signatures. So what it thinks a virus looks like, the kind of things it does, the kind of code in it, then it will try and find an existing virus and then do something about it. Heuristic checks are used by virus checkers. So suspicious behavior of programs can be flagged. It doesn't just have to say it's the exact match, but if it's sort of doing things that look strange, look odd, then it can flag that. Quarantine is isolating the infected file so it can't run or spread any further. So the files haven't been deleted, they haven't been removed completely, but they're isolated so they can't actually run anymore. And then you may delete them or repair the system. So removing the virus and repairing some of the damage would be part of the delete repair part section there. And we have to update this software very regularly because new viruses are appearing all the time. So we need to update that signature database to give it a chance to identify these new viruses that are coming out. And it's important for virus checking software to be running in the background, not just when you manually decide to do a scan. And it's also really important for it to have auto updates rather than manual updates, so you don't have to remember to do updates to the antivirus software. The next utility we've got is file compression. So the idea here is just reducing the file size to use less storage, you have faster transmission using less bandwidth. And as we've seen before in the data representation section, I think it was, we've got lossless and lossy compression. So remember, in lossless, no data is lost. We can restore the original file exactly as it was. It works by removing redundancy, i.e. data you don't actually need to store, for example, run length encoding and dictionary coding. We use that for things like text spreadsheets, program code, and archives. And lossy compression permanently discards some of the data, for example, data that we can't really notice with our eyes or hear with our ears. This gives much smaller file sizes usually than lossless compression, but you can only use it for certain kinds of files where that loss of data isn't critical. So for example, images, audio and video. Then we've got backup software. So to back up means to make a copy of, and backups are data that you might need again. So it's slightly different to archives. Archives is data that you don't think you're going to be needing anymore, but a backup is data that you do need. If you were to lose the original, you would need to go to your backup. You might lose data, it might be damaged, it could be hardware faults, it could be accidentally deleted, it could be damaged or corrupted by malware or stolen, physically stolen. And backup software is an automated process, or should be an automated process, so you don't forget to do it. Copies should be kept on separate devices, obviously because of things like hardware faults. It can be kept in the cloud, so it's physically very far away or separate from the original. It allows the user to select what files and folders should be included in backups, and it supports the restoring of individual files or a whole system to an earlier state. There are different kinds of backups. A full backup, if you run a full backup, it'll copy every single thing that you want. It's slow, but the simplest to restore, so you just restore the whole thing. Incremental backups, they copy only the things that have changed since the last backup of any kind. So any kind of backup you've done, it's going to say what was changed since then, and it only copy that. So they're fast because they're only doing a small amount of data normally. But then again, it's slower to restore because you have to look at multiple incremental backups to get back the whole picture. And then differential copies everything that's changed since the last full backup. So only the changes since your last full one. And then obviously you'll hopefully do another full one, and then you can go back to just having no differential until things start changing, and then the differential starts building up again. So to get back the whole system, for example, you need to go back to the last full one plus any differentials since that one. Then we have program libraries. So program libraries are software that we can use when we're developing our own code. It's really useful to be able to use existing pre-written code. It's been pre-written, pre-compiled, it's been tested before, so the developer can just call it from their own program instead of having to write that code themselves. That saves them a lot of time. So a library consists of things like subroutines, functions, classes and objects. Obviously that's for object-oriented programming. that we'll look at later. It may have constants, data structures, predefined data types, and so on. So anything you might need that you could make pre-made could be stored in a library. So libraries exist for an awful lot of things like maths, graphics, algorithms like sorting, searching algorithms, encryption network, and so on. Languages like Python, for example, have huge amounts of libraries available that can do all kinds of things. So how do they get used? Well, the developer will usually import or link to the library. They'll call the subroutines with some parameters, or they'll call it with arguments that become parameters. And they don't need to know how that code works. They don't need to understand the internals. All they need to understand is the interface they use to access it. So dynamic link library is code that's linked at runtime. So not when you're compiling it, but it's only brought in when you're actually executing. So in static linking, if you're using library code, that code is copied into the executable. So the executable will be larger. It was your code plus all the library code that you've included. And that whole thing is loaded into memory, even if you don't actually use it. And updating the library means that you have to recompile your programs, because a change in the library code would not be reflected in your program execution if you didn't recompile it. So compare that with dynamic linking. So the dynamic link library is a separate file. It's not part of the executable. It's only loaded into memory when it's actually needed at runtime. So if your program doesn't call the code, then it doesn't need to be loaded into memory, which obviously saves memory. It also means the executable files are smaller because they don't contain the library code, only your code. It means that one dynamic link library can be shared by several programs running at the same time. So if it is loaded, then multiple programs can be using it at the same time without having to have duplicate copies of it in memory. The dynamic link library can be updated, and then you don't need to have to update your program. It will automatically start using the new code whenever your program runs. So for the developer, the benefit is that it's faster. They can just write their code and then use code that's already been written and tested without having to write it themselves. That code's normally reliable, it's well tested, it's been debugged already, so it's ready to go. It's often written by specialists, and they know what they're doing. They've made efficient code. They've made code that works very well. The developer themselves may not be able to do such a good job on that code. And it allows the developer to concentrate on the unique parts of their own program. So the things that they're really concerned with are not something that's, secondary to what they're doing. It reduces the development cost because they're spending less time doing the coding, and there's less errors and less testing required. Keeping the executable smaller and allowing it to be shared between programs. Now the drawbacks, the source code may not be available, so it cannot be adapted, so you don't have access necessarily to the library, so you can't change and adapt the code. The code may contain far more than you actually need, or it may not be an exact fit, so it's a compromise if you're using it, and it's a bit bloated in that it has more than you actually need. If that DLL goes missing, then your program will fail, it can't run. Obviously with static linking you've already compiled code that's not going anywhere, so if the original programs go missing it doesn't affect your compiled version. But with the dynamic link library your program will fail if the dynamic link library is missing or corrupted. And they may change the library in such a way that's no longer compatible with your program. You may not have any direct control over that, and therefore your code may fail one day just because somebody else has changed the library. Also, DLLs are a bit of a security risk. They could be compromised. You don't actually know the code in them, so you don't know exactly what it's doing. You're just trusting that it's a safe library to be using. And there may be some licensing cost or restrictions in the way that you can use the library. So, in summary, the operating system is the interface between users' applications and the hardware. There are 5 key management tasks of the OS. So memory, file, security, hardware, and process. And remember the MFSHP. My files should have priority. Utilities keep it healthy, making sure the system runs smoothly and efficiently. So things like disk formatters, virus checkers, defragmentation software, disk analysis and repair, compression, and backups. And then libraries save developers time developing code. So they have pre-written, pre-tested code. Dynamic link libraries link at runtime. This keeps the executable small and they can be shared as well. Alright, so that's the end of 5.1, the operating system section.